Hello students, this is Dr. K.K. Bisht from Department of Chemistry, RCU Government PG College, Uttarkashi. In this video, I will introduce you with the concept of spectroscopy. This lecture will be useful for B.Sc 6th SEM students of HNB Garhwal University and associated colleges. So let us start. Spectroscopy is a modern tool to characterize any unknown substance, and it involves study of interaction of electromagnetic radiations with matter. Depending on the type of electromagnetic radiation being used, spectroscopic techniques are named as UV visible spectroscopy, IR spectroscopy, microwave spectroscopy, and so on. Now the question is how the electromagnetic radiation and matter interact with each other. To answer this question, let us focus on some properties of electromagnetic radiations. Electromagnetic radiation is oscillating electromagnetic wave comprising of packets of energy called photon or quanta. Energy of electromagnetic radiation is defined by equation E equals to h nu, which is further equals to hc upon lambda, where h is Planck's constant, nu is frequency of the radiation, c is speed of light in vacuum, and lambda is the wavelength of radiation. So this equation suggests that higher the value of lambda, lower will be the energy of radiation, and vice versa. Or we can say higher the value of frequency nu, higher will be the energy of radiation. In fact, we have a broad spectrum of electromagnetic radiations, of which visible radiation or visible light is a very small section. In this scheme, different electromagnetic radiations are placed in their decreasing order of energy from left to right. For our reference, let us note here that wavelength of visible radiation is approximately 400 to 800 nanometer. Wavelength for infrared radiation ranges from 2.5 micrometer to 25 micrometer. That for microwave and radio waves are of the order of millimeter and meters respectively. Wavelength of ultraviolet is smaller than 400 nanometer, and that for X-rays is of the order of angstrom. Since we have to study UV visible and IR spectroscopy, we will be focusing on that part only. Let us also put the conversion factors for different units mentioned here. 1 millimeter is equal to 10 raised to power minus 3 meter, 1 micrometer is equals to 10 raised to power minus 6 meter, 1 nanometer is 10 raised to power minus 9 meter, and 1 angstrom is equals to 10 raised to power minus 10 meters. So now it is clear that the photons of a given wavelength of a particular electromagnetic radiation carry discrete amount of energy defined by the equation E equals to h nu. Now let us come back to the question, what happens when the matter and electromagnetic radiation interact? In fact, there are many possibilities. Radiation which is striking on a matter may get absorbed, it may get reflected, it may get transmitted, or it may get scattered, and sometimes a different radiation of different wavelength may get emitted. So many possibilities are there, but the spectroscopic techniques that we need to study in our curriculum are originated from the phenomena of absorption. So we will be focusing on this aspect of interaction only. Now, before going further, let us understand matter comprises of molecules or atoms or ions. In order to interact with electromagnetic radiation, these molecules, atoms or ions must possess non-degenerate energy states. Non-degenerate means two or more energy states or levels are having unequal energies. Molecules generally have non-degenerate electronic, vibrational and rotational energy levels, which are also defined as quantized energy levels. The term quantized means that a molecular transition between two energy states could happen with transaction of one and only one photon. Suppose this energy gap here is of 10 kilocalorie, then we require one photon of exact 10 kilocalorie energy to exercise or to excite this molecule from this lower level to this higher level. It won't accept a sum of two electrons of 5 kilocalorie each or any other such arithmetical combinations. Now that we know that energy states of molecules are quantized and the fact that electromagnetic radiation is also quantized, we can choose a suitable wavelength of an electromagnetic radiation to get a molecule excited. Alternatively, we can say that if we know what wavelength a molecule has absorbed, we can fetch the information about the energy levels present in the molecule, which will ultimately give us information about the nature of molecule. It will help us to characterize it or to identify it. So, for a given molecule, energy gap of electronic, vibrational and rotational levels follow following relation. Energy gap of electronic levels is higher than the energy gap of vibrational levels, which is further higher than the energy gap of rotational levels. So energy required for electronic transitions is highest one among all three, then the energy required for vibrational transitions, and then the energy required for rotational transitions. Energy required for electronic transitions is equivalent to energies of UV and visible radiations. Hence, electronic transitions can be effected by UV visible radiation. So if we supply a sample or a molecule with some UV visible radiation, a suitable electronic transition may take place in that molecule. Similarly, IR and microwave offer suitable energies for vibrational and rotational transitions to occur. It is further important to note that electronic transitions offer information about unsaturation and conjugation in organic molecules, and infrared spectroscopy offers information about bond vibrations, which can eventually help us to identify the functional groups present in the molecule. So we will be discussing details of electronic spectroscopy, that is UV visible spectroscopy, and the IR spectroscopy, which is the part of vibrational spectroscopy, in the subsequent lectures. Thank you for your attention.